There's a machine out there, right now, tumbling through the absolute darkness between the stars. A machine built by human hands nearly 5 decades ago, powered by technology that existed before the personal computer, before the internet, before most of the people watching this were even born. It is older than entire governments. It is farther away than any object humanity has ever created. And in the last few years, it has been sending back data that is quietly dismantling everything scientists thought they knew about the edge of our solar system, the nature of interstellar space, and the protective shield that stands between Earth and the raw, violent radiation of the galaxy itself. Nobody is talking about what it found, but they should be. Think about that for a moment. A spacecraft launched in 1977, a year when disco was on the radio and the most powerful computers on Earth filled entire rooms and could barely run a word processor. Engineers at NASA built 2 machines, loaded them onto rockets, and aimed them at the outer planets. Not with any sophisticated digital guidance system, not with artificial intelligence, not with any of the technology we now consider basic. They did it with mathematics, pure, elegant mathematics. And those 2 machines, Voyager 1 and Voyager 2, have been traveling through space every single second since then, never stopping, never slowing down in any meaningful sense, just drifting outward through the void at roughly 34,000 miles per hour, which sounds fast until you realize how incomprehensibly large space actually is. But here's where it gets interesting, because for most of those decades, Voyager 2 was treated almost as the backup, the secondary probe. Voyager 1 crossed into interstellar space first, back in 2012, and that was the headline, that was the history-making moment, that was the story the world celebrated. Voyager 2 followed 6 years later in November of 2018, crossing the heliopause, that invisible but enormously significant boundary where the sun's influence ends and the true interstellar medium begins. And the scientific community erupted. But what happened after that crossing, what Voyager 2 has been quietly transmitting back across 12 to 16 billion miles of empty space ever since, is a story that has not been told with the gravity it deserves. Scientists had their first real look at the heliopause in 2012 when Voyager 1 entered interstellar space, and what they began to see left them scratching their heads. The interstellar magnetic field turned out to be 2 to 3 times stronger than expected, meaning interstellar particles were exerting up to 10 times the pressure on our heliosphere than anyone had previously calculated. 10 times. That is not a minor miscalculation. That is not a rounding error in some laboratory model. That is a fundamental misunderstanding of the forces pressing in on our solar system from every direction, every single second of every single day. And that revelation, as staggering as it was, turned out to be only the beginning. The real story is what Voyager 2 found when it crossed that same boundary 6 years later. And to understand why Voyager 2's crossing was so much more scientifically valuable than Voyager 1's, you need to understand one critical difference between the 2 spacecraft. Voyager 2 carries a working plasma science experiment, an instrument that stopped functioning on Voyager 1 all the way back in 1980, long before that probe crossed the heliopause. Think about what that means. When Voyager 1 made its historic crossing, scientists were essentially flying blind when it came to plasma data. They could observe the crossing through other instruments, magnetic field sensors, cosmic ray detectors, but the ability to directly measure the temperature, density, pressure, and behavior of plasma at that boundary was simply gone. When Voyager 2 crossed the heliopause, it was carrying that instrument, a functioning plasma experiment, operating in the most remote location any human-made object had ever reached. And what it measured when it got there defied expectation after expectation. For the first time in human history, researchers could directly observe that as an object approaches within 140 million miles of the heliopause, the plasma surrounding it begins to slow, heat up, and grow more dense. And on the other side of that boundary, in the interstellar medium itself, the temperature of the plasma was measured at least 54,000 degrees Fahrenheit, far hotter than scientists had predicted. Let that number sink in. The space between stars, which most people imagine as a silent, cold, near absolute zero void, is filled with plasma that burns at 54,000 degrees. Now, this plasma is extraordinarily thin and diffuse, so thin that despite its temperature, a human being floating in that region would still freeze to death because there are so few particles to actually transfer that heat. But the temperature itself, the pure energetic state of that interstellar medium, was shockingly, unexpectedly high, and nobody had predicted it. This is not chaos. This is the universe telling us something, and we have been too focused on other things to listen. The plasma data from Voyager 2 revealed a boundary region with a width of approximately 1.5 astronomical units before the heliopause itself, a zone where the plasma slows, heats up, and becomes twice as dense as typical heliosheath plasma. And then, just 0.06 astronomical units inside the heliopause, a much thinner and more sharply defined boundary layer was detected, where the radial speed decreases and both density and magnetic field intensity spike dramatically. The entire heliopause transition from one regime of space to another occurred in less than a single Earth day, one solar rotation, one Earth day. And the spacecraft went from the edge of everything our sun controls to the vast, ancient, uncharted medium between the stars. The sharpness of that transition, the sudden clarity of that boundary, overturned yet another model. Scientists had theorized a more gradual crossing, a slow fade from one environment to the next. Instead, Voyager 2 found something almost architectural in its precision, a wall, not a gradient. And this is where everything changes, because here is what the mainstream coverage of these discoveries consistently fails to address. The heliopause is not simply a boundary between two different environments. It is the protective shell of our entire solar system. Everything you have ever known, every planet, every moon, every asteroid, every human life ever lived, all of it exists inside this bubble. Voyager 1 already established that the heliosphere protects Earth and the other planets from more than 70% of the galactic cosmic radiation that constantly bombards it from outside. 70%. That means without the heliosphere, without the sun's protective bubble of magnetic fields and plasma, the radiation environment across the inner solar system would be catastrophically different. Life as we know it, quite possibly, could not have emerged at all. The heliosphere is not a background detail of astronomy. It is the reason we exist. And now, Voyager 2 has given us direct evidence that this protective shield is under far more pressure than we ever realized, pressed upon by an interstellar medium that is hotter, denser, and magnetically stronger than our best models predicted. What does that mean for the long-term stability of our heliosphere? What does it mean that the interstellar magnetic field is 2 to 3 times more powerful than expected, exerting forces that push in on the sun's bubble from every direction? These are not questions being asked loudly in the popular press, but they are being asked in physics journals, in JPL briefings, in the quiet back offices of heliospheric research teams who understand exactly what these measurements imply. But wait, because the discoveries do not stop at the heliopause itself. What Voyager 2 found about the behavior of particles and matter at that boundary introduced a new mystery that scientists are still grappling with. Before Voyager 1 passed through the heliopause, it traveled through tendrils of interstellar particles that had punched into the heliosphere like tree roots through rock. Voyager 2 saw something different, a trickle of low-energy particles that extended more than 100 million miles beyond the heliopause in the other direction, leaking outward from the solar system into interstellar space. The leaks go both ways. The heliopause is not a sealed container, it is a permeable border, and material from our solar system is escaping into interstellar space while interstellar material is penetrating inward. The exchange is slow, but it is constant. And the implications of a leaky heliosphere in terms of the long-term composition of the region around our sun are something scientists are still working to fully understand. Then there is the mystery of the magnetic field alignment, which is perhaps the most quietly stunning discovery in the entire Voyager dataset. When Voyager 2's magnetometer analyzed the magnetic field in the region just beyond the heliopause, it confirmed a result that had first puzzled scientists when Voyager 1 detected it. The magnetic field in interstellar space just outside the heliosphere appears to run parallel to the magnetic field inside the heliosphere. With Voyager 1, scientists had only one data point and couldn't determine whether this was a genuine pattern or a coincidence. Voyager 2's observations confirmed it. The two fields align. Think about what that means. The magnetic architecture of our solar system and the magnetic architecture of local interstellar space appear to be oriented in the same direction. They are not colliding fields running at chaotic angles, they are aligned. And that alignment, far from being a reassuring coincidence, raises a profound question. Why? Is it a product of how our solar system formed within this particular region of the galaxy? Is it evidence of large-scale galactic magnetic structures that we have only begun to understand? The data exists. The answer does not yet. Read that again. The answer does not yet exist. One of humanity's most fundamental questions about our place in the galaxy, how our solar system's magnetic signature relates to the magnetic signature of the interstellar medium around it, remains open. And the only instrument that can provide direct measurement of this is a 47-year-old probe running on nuclear battery power, transmitting at a rate of 160 bits per second across a distance so vast that its signal takes more than 16 hours to reach Earth, even traveling at the speed of light. Now consider the timeline of this mission in human terms, because it reframes everything. Voyager 1 and Voyager 2 were launched just 16 days apart in 1977. designed to take advantage of a rare alignment of the outer planets that occurs only once every 176 years. 176 years. The engineers who designed these missions understood that the planetary alignment, enabling a single spacecraft to visit Jupiter, Saturn, Uranus, and Neptune through sequential gravity assists, would not come again for nearly 2 centuries. They had one window, one launch window across an entire human civilization's worth of time. And they hit it. Voyager 2 remains the only spacecraft to have studied all 4 of the solar system's giant outer planets at close range. It discovered a 14th moon at Jupiter, was the first human-made object to fly past Uranus, where it discovered 10 new moons and 2 new rings, and became the first to fly past Neptune, where it revealed 5 moons, 4 rings, and the Great Dark Spot. All of that, an entire catalog of planetary discovery that would have taken dozens of separate missions to replicate, was accomplished by a single spacecraft, using nothing more than the gravitational pull of the planets themselves as fuel. But here is where it gets worse. Or rather, here is where the situation becomes urgent in a way that most coverage ignores entirely. Voyager 2 is dying, not metaphorically, not in the distant future sense that we can defer thinking about. It is actively losing the ability to function, and the clock is running in real time. In October 2024, NASA announced that the plasma science instrument, the very instrument that had provided those unprecedented measurements of the heliopause and the interstellar medium, had been turned off permanently to conserve power for the remaining 4 instruments. The instrument that made Voyager 2 uniquely valuable, the tool that no other spacecraft in history had managed to operate at the edge of interstellar space, is gone, switched off. Not because it failed, but because the spacecraft no longer has enough power to run it. This is a moment of genuine, irreversible loss for human scientific knowledge. Every measurement that plasma instrument could have taken from this point forward, every data point about how the interstellar medium changes with increasing distance from the heliosphere, every confirmation or contradiction of our models about the structure of the outer solar system, is now permanently unavailable. We will never get that data. Not from Voyager 2, not from any other mission, because the only proposed follow-up mission specifically designed to study the outer heliosphere and interstellar medium, known as the Interstellar Probe, was not recommended as a priority in the most recent decadal survey for heliophysics released in 2024, effectively eliminating the near-term possibility of direct in-situ measurements of the interstellar medium anytime soon. The window is closing, and the scientific community knows it. What most people are not seeing is the compounding nature of this loss. It is not simply that one instrument on one spacecraft has been turned off. It is that Voyager 2 represents a category of scientific access that took 47 years to achieve and cannot be replicated quickly. The physics of reaching the heliopause and beyond are brutally unforgiving. Even New Horizons, NASA's most recent deep space probe, which famously flew past Pluto in 2015 and is currently surveying the Kuiper Belt, is on course to cross the heliopause itself, but that crossing is perhaps a decade or more away. A decade. And by that point, the interstellar medium will have continued to evolve. The heliosphere will have responded to solar cycle activity in ways we are still learning to model, and the questions Voyager 2's dying instruments are leaving unanswered will have grown larger, not smaller. According to informed sources in heliospheric research, the data being returned right now, in these final operational years of the Voyager mission, carries extraordinary scientific weight precisely because of what Voyager 2 confirmed about the structure of the heliosphere's boundary. Research published in early 2024 now suggests that the heliopause itself may be shaped differently than previously believed. Not a thin boundary line, as scientists had modeled for decades, but instead a thick boundary layer, one that forms where the magnetic fields of the heliosphere and interstellar space interact. And critically, until Voyager 2 crosses this full transitional zone, scientists argue it has not yet reached the pristine interstellar medium. The spacecraft crossed the heliopause in 2018, but it may still not be in true interstellar space. The definition of where our solar system ends and genuine interstellar space begins is still, in 2025, being written. It is not settled science. It is an active frontier. Think about what that means for every science textbook ever written. Every diagram showing the solar system with a clean outer edge. Every curriculum that teaches students that the heliopause is the clear boundary of our cosmic address. All of it may be oversimplified to the point of being misleading. The real boundary of our solar system is not a line. It is a region, a thick, complicated, magnetically turbulent region that behaves differently depending on where you cross it, when you cross it in the solar cycle, and what instruments you bring to measure it. Voyager 1 crossed at a different location and during higher solar activity than Voyager 2. Scientists expected the heliopause to move outward or inward as solar activity changes, like a lung expanding and contracting with breath. And the big surprise was that both probes encountered the heliopause at nearly the same distance from the Sun, despite their crossings occurring at opposite phases of the solar cycle. And nobody can fully explain why. This is a mystery at the largest scale our instruments can currently measure, and it has no answer yet. The further you go with Voyager 2's data, the more the universe reveals itself to be not simpler than our models predicted, but dramatically more complex. As of 2025, Voyager 1 and Voyager 2 have now reached heliocentric distances of approximately 172 and 143 astronomical units, respectively. Both spacecraft are now traveling through what scientists call the outer heliosheath, a region of interstellar space that is perturbed by the presence of the heliosphere, where plasma flows are significantly decelerated and heated by global compression processes. They are not yet in undisturbed interstellar space. They are in a transition zone, a region where the heliosphere's influence still echoes outward, and where the data being collected is unlike anything obtainable from Earth-based observation. Every astronomical unit of additional distance those probes travel before their power fails is irreplaceable scientific territory. And this points to something that the immediate coverage of Voyager milestones consistently misses: the cumulative strategic importance of what this mission represents for humanity's understanding of where we live in the galaxy. We know, in broad terms, that the Sun orbits the center of the Milky Way. We know that this orbit carries the entire solar system through different regions of the galaxy over vast timescales. Astronomers have recently confirmed, for example, that the solar system traversed the Orion star-forming complex approximately 14 million years ago. 14 million years ago, our solar system was passing through an entirely different neighborhood of the galaxy, surrounded by different interstellar medium, exposed to different radiation environments, potentially with a heliosphere shaped very differently than the one we currently inhabit. The conditions under which life on Earth has evolved over the past hundreds of millions of years have not been constant. The protective bubble has been changing. Its shape, its strength, its interactions with the surrounding medium, all of it has varied across geological time. And the only way to truly understand the heliosphere's current state, to take its real-time measurements rather than indirect inferences, is through missions like Voyager. Now, layer on top of that this fact. Both Voyager spacecraft continue to measure electron density by detecting radio waves generated when solar eruptions cause electrons in the interstellar medium to oscillate, and current measurements indicate that interstellar density has continued to increase further from its value just outside the heliopause. And no one fully knows what will happen next. The density of the medium surrounding our solar system is not static. It is evolving. Whether this represents a long-term trend, a cyclical variation tied to the solar cycle, or something else entirely, is a question that requires continued observation to answer. And the observational window is closing. There is a phrase that keeps appearing in the scientific literature on Voyager, a phrase that captures the strange, almost melancholy quality of this moment in space exploration. Scientists who have dedicated their entire careers to this mission describe it as irreplaceable. Not simply important, not merely historic, irreplaceable. One senior scientist who has worked on Voyager for their entire professional career noted simply, "I actually plan to retire with Voyager." That single sentence carries more weight than any press release. It speaks to the depth of connection between the people who built this mission, who have monitored it, troubleshot it, nursed it through power failures and instrument shutdowns and the unimaginable distances of deep space communication, and the spacecraft itself. There is something profoundly human about a probe that has outlasted careers, outlasted entire eras of technology, outlasted cultural epochs, and is still transmitting from beyond the edge of the solar system. But the humanity of the mission does not soften the scientific urgency, because the discoveries Voyager 2 has already made carry implications that extend far beyond the current mission, into questions about planetary protection, about the long-term habitability of Earth, about the conditions under which solar systems like ours can support life. The heliosphere is not a static feature of the cosmic landscape. It is dynamic, responsive, and, as Voyager 2 has shown us, far more complex at its boundaries than our best models had described. The plasma inside the heliosphere is hot and sparse, while the plasma in interstellar space is colder and denser in general terms. But the boundary between these two regimes is a battleground of pressure, magnetic forces, particle exchange, and temperature gradients that shifts constantly as both the solar wind and the interstellar medium fluctuate. Understanding that battlefield is not an academic exercise. It is foundational knowledge about the environment our planet has inhabited for 4.5 billion years. And there is one more layer to this story, one final discovery from Voyager 2's data that deserves to be stated with full clarity. The new papers confirming Voyager 2's interstellar status make clear that the spacecraft is not yet in undisturbed interstellar space. Like its twin, Voyager 2 appears to be in a perturbed transitional region just beyond the heliosphere, a zone that has not yet been fully characterized or Understood. Which means that even now, even with the plasma instrument turned off and the power slowly declining, Voyager 2 is traveling through territory that has never been directly explored, sending back data from a region that cannot be observed in any other way, contributing to a map of the solar system's outer boundary that humanity has been trying to draw for over half a century. The golden record sits aboard Voyager 2 right now, that gold-plated disk carrying music, greetings, images, and information from Earth, a message in a bottle thrown into the cosmic ocean in 1977. If another intelligence ever intercepts it, billions of years from now, long after the sun has expanded, and Earth has been consumed, the record will still be there. A relic of a species that looked up at the stars and sent a piece of itself outward into the dark, armed with mathematics and curiosity and the stubborn conviction that going further, finding out more, asking harder questions, was worth every ounce of effort it required. The mission is ending. Not today, not next year. But the instruments are failing one by one, the power is declining at a rate of about 4 watts per year, and the timeline for final communication is now measured in years rather than decades. Experts are cautiously optimistic that the Voyager spacecraft will remain communicable through their 50th. Birthday's in 2027, but their end will eventually come. And when their instruments fail, they will continue on their trajectories for billions of years to come, drifting silently through interstellar space long after the civilization that built them has changed beyond recognition. What will we have learned by then? What questions will Voyager 2's final transmissions leave open? Will the interstellar density continue to increase? Will the heliosphere's boundary prove stable, or will future observations from the ground, from IMAP, from instruments not yet built, reveal that the protective bubble we inhabit is more variable, more vulnerable, more surprising than even Voyager's groundbreaking data has shown? Here is the honest answer. We do not know. We do not yet know the true shape of the heliosphere. We do not fully understand why the heliopause was encountered at the same distance by both probes despite different solar conditions. We do not know why the magnetic fields align. We do not know the exact boundary of pristine interstellar space. We do not know what Voyager 2 would have measured if its plasma instrument had survived another decade of operation. And we do not know whether humanity will build another mission capable of answering these questions before the gap in knowledge grows too large to bridge from a distance. What we do know is this. 47 years ago, a group of engineers and scientists aimed a machine the size of a compact car at the distant stars and launched it on a trajectory that no human object had ever traveled. That machine is still out there, still sending signals, still taking measurements in a place no other instrument will reach for years. And what it has found, a boundary hotter than predicted, a magnetic field aligned against all expectation, a heliosphere leaking both inward and outward, an interstellar medium denser and more pressurized than our models described, tells us that the universe beyond our solar system is stranger, more complex, and more urgently in need of understanding than we have allowed ourselves to admit. The biggest discovery Voyager 2 has made may not be any single measurement. It may be this, that the edge of our solar system is not an ending. It is a question, and we are only just beginning to understand how to ask it.